March 26, 2012, filmmaker James Cameron squeezed himself into a cramped 7-foot sphere welded to the front of a vertical torpedo. The submersible was called Deep Sea Challenger, lime green, ungainly, 24 feet tall, purpose-built for a single mission to reach the deepest point in the ocean. The Challenger, deep at the bottom of the Mariana Trench, 35,756 feet below the surface of the Pacific Ocean, nearly 7 miles straight down. The descent took 2 hours and 36 minutes, sinking through layers of ocean that grow progressively darker, colder, more hostile. The pressure outside the capsule increasing with every foot. By the time Cameron reached the bottom, the water pressure was bearing down on his tiny sphere with a force of 8 tons per square inch. 16,000 pounds pressing on every square inch of the hull. 1,100 times greater than the pressure at sea level. Enough to crush a human body into paste in a fraction of a second. But Cameron wasn't thinking about the pressure. He was thinking about what he was seeing through the small viewport. The barren, pale sediment plain stretching away into darkness. The finest particles of marine snow drifting down like ash. The complete and utter silence. The loneliness. He was the first human being to reach this place alone. The third person in history to reach it at all. And then he saw it, lying on the sediment. Small, innocuous, impossible to miss because of what it was. A plastic shopping bag, translucent, probably from a grocery store, sitting at the deepest point on Earth. The furthest you can go down on this planet without drilling into the rock. Cameron's first thought, he'd later say, was pragmatic. Annoyance. This was supposed to be the last pristine place. The final frontier. 7 miles down. 11 kilometers. Deeper than Mount Everest is tall. A place so remote, so extreme, that nothing human should have been able to reach it before dedicated exploration. And yet, there it was. A piece of trash. Our trash. Humanity's calling card. We'd gotten our garbage to the bottom of the ocean before we'd gotten our second human down there. Because here's the thing. When Jacques Piccard and Don Walsh made the first descent to Challenger Deep in 1960, 52 years before Cameron, they spent 20 minutes on the bottom. 52 years and only 2 other people. But in that same half-century, our plastic waste had made the journey thousands, maybe millions of times, passively, effortlessly, sinking through the water column, year after year, accumulating in the one place on Earth we thought was untouchable. That plastic bag wasn't just pollution evidence. It was a symbol, a message from the abyss. We can reach anywhere. We can contaminate anything. And we're doing it faster than we can understand what we're destroying. If you're fascinated by the hidden stories of Earth's most extreme places, please consider subscribing. Your support helps us continue exploring these forgotten frontiers. Thank you. The Mariana Trench is not a single trench. It's a system, an arc-shaped scar in the Pacific seafloor stretching for over 1,500 miles from southeast of Japan to north of Papua New Guinea. It marks the boundary where the Pacific Plate is being forced beneath the smaller Philippine Plate. Subduction. The Pacific Plate, older and denser, dives beneath its neighbor and descends into the mantle, creating a deep V-shaped chasm in the crust. The deepest part of this system is called Challenger Deep, named after the HMS Challenger, the British survey vessel that first measured extreme depths in the area in 1875 using weighted sounding lines. The Challenger expedition didn't reach the absolute deepest point, but they established that the Mariana region was extraordinarily deep. Deeper than anyone had imagined. Modern measurements using multi-beam sonar and pressure sensors place the deepest confirmed point at 10,994 meters, 35,756 feet. To put that in perspective, if you placed Mount Everest, the tallest mountain on Earth, at the bottom of Challenger Deep, its peak would still be over a mile underwater. The trench is deeper than the height of commercial airliners' crews. If you dropped a steel ball from the surface, it would take over an hour to hit the bottom. But what makes the Mariana Trench truly alien isn't just the depth, it's what that depth creates. Because at the bottom of the trench, the environment is so extreme, so fundamentally different from the surface world, that it might as well be another planet. And we're only just beginning to understand what lives there, and what we've already done to it. Let's start with something unexpected. The trench is loud. When the National Oceanic and Atmospheric Administration deployed titanium-hulled hydrophones into the Challenger Deep in 2015, they expected silence. The assumption was that 7 miles down, isolated from surface noise, cut off from most biological activity, the deep would be a place of profound quiet. The quietest place on Earth, perhaps. An acoustic void. They were completely wrong. The trench is a cacophony. The hydrophones recorded constant noise, a rumbling, groaning, creaking soundscape that never stops. Earthquakes. Constant, low-frequency seismic activity as the Pacific Plate grinds beneath the Philippine Plate. The plates don't slide smoothly. They stick and slip. Every slip sends shockwaves through the rock and water. At Challenger Deep, you're sitting directly above one of the most seismically active zones on the planet. The Earth itself is growling. But it's not just earthquakes. The hydrophones picked up biological sounds, whale songs. Baleen whales calling to each other across vast distances. Their low-frequency calls traveling through what's called the deep sound channel, a layer of the ocean where temperature and pressure create a natural waveguide. Sound can travel for thousands of miles through this channel without losing much energy. The hydrophones at Challenger Deep were picking up whales that were hundreds, even thousands of kilometers away. The trench acts like a giant amplifier, a passive sonar array. Everything that makes noise in the Pacific, if it's low frequency enough, eventually reaches the trench. Ship propellers. The hydrophones recorded the rhythmic thrum of distant shipping traffic. Hundreds of ships churning through the surface waters far above, their propeller noise propagating down through the water column and reaching the bottom. Even at 7 miles depth, human activity is audible. We are never truly absent. And then there were the unidentified sounds, sounds that didn't match any known source. Metallic clanks, rhythmic tapping, organized sequences of clicks that sounded almost artificial. Biological? Geological? Equipment malfunction? No one knows. The deep ocean is full of mystery sounds, calls and noises that have been recorded but never explained. And the Mariana Trench is one of the richest sources. But one sound recorded in 2014 stands out. NOAA researchers called it the Western Pacific Biotwang, a bizarre 5-part call that starts as a low baritone moan and then suddenly leaps upward into a metallic twanging sound. like someone plucking a giant steel cable. It doesn't match any known whale call, doesn't match any known fish, doesn't match seismic activity or human equipment. The leading hypothesis is that it's a minke whale, a type of baleen whale that's poorly studied because they're difficult to observe. Minke whales are known to produce strange variable calls, and they are present in the Western Pacific. But here's the problem. No one has ever directly observed a minke whale making this sound. The correlation is based on overlapping locations and timing. It's an educated guess, not proof. And some researchers aren't convinced it's biological at all. The metallic twang doesn't sound organic. It sounds mechanical, like metal under stress. Could it be related to underwater infrastructure? Submarine communication cables, which crisscross the Pacific floor, sometimes near the trench? Possible. But why would a cable make a call with such a specific repeating structure? Why would it moan first and then twang? Cables don't moan, so the mystery persists. The Western Pacific Biotwang joins a list of unidentified ocean sounds that have haunted marine biologists for decades. The bloop, the Julia, the upsweep, slow down, all recorded by hydrophone networks, all eventually explained, mostly as ice shelf fractures or volcanic activity. But some, like the biotwang, remain ambiguous, probably natural, probably biological, but not certain. And this raises an uncomfortable question. If we can't identify the source of a sound recorded by sensitive equipment in one of the most studied deep ocean regions, what else is down there that we're completely missing? Here's something most people don't know. The hydrophone network that recorded these sounds wasn't originally designed for science. It was designed for war. During the Cold War, the United States Navy deployed a vast network of underwater listening stations called SOSUS, Sound Surveillance System. Arrays of hydrophones placed on the ocean floor, connected by cables to shore stations. The purpose was to detect Soviet submarines. The deep sound channel, that natural waveguide we talked about, made it possible to hear submarines thousands of miles away. If a Soviet sub left port, SOSUS would hear it. The network was highly classified. Its existence wasn't acknowledged until the 1990s, after the Cold War ended. And even then, not all of it was declassified. We know some SOSUS arrays were placed in the Atlantic, along the SOSUS barriers near Greenland, Iceland, and the UK. We know others were placed in the Pacific, but exact locations, capabilities, how much of the network is still active? That's still classified. What we do know is that some arrays were placed near or within the Mariana Trench. The trench's position in the Western Pacific made it strategically valuable. Soviet subs operating in the region could be monitored. The trench's extreme depth and acoustic properties made it an ideal location for passive sonar. You could hide equipment there in the deepest, most inaccessible place and listen to half the Pacific. After the Cold War, some SOSUS arrays were repurposed for scientific research. NOAA took over operation of several, using them to study whale populations, seismic activity, and oceanographic phenomena. The data from these arrays has been invaluable, but not all arrays were handed over. Some remain under Navy control, and the question remains, are we still listening? Is the Navy still monitoring the trench? And if so, what have they heard that hasn't been shared? Because if the unclassified hydrophones are picking up mystery sounds, what are the classified ones hearing? What data exists in Navy archives that scientists will never see? It's a frustrating reality of deep ocean research. The best equipment, the most sensitive listening devices are often military, and their data is locked away. We're trying to understand the least known environment on Earth with one hand tied behind our back. The ocean keeps its secrets, and so does the military. But let's go back to the beginning, back to 1960, because before we could listen to the trench, we had to reach it. And the story of the first descent is one of the greatest adventure stories in history. It's also, arguably, one of the most insane. January 23rd, 1960, Guam. A small island in the Western Pacific. A Swiss scientist named Jacques Picard and a US Navy lieutenant named Don Walsh are preparing to climb into a submersible called Trieste. The Trieste is not sleek. It's not elegant. It looks like a blimp underwater. A massive float filled with gasoline for buoyancy, with a tiny steel sphere bolted to the underside. The sphere is the pressure hull, 7 feet in diameter, barely big enough for 2 men sitting shoulder to shoulder. The walls are 5 inches of forged steel. The single viewport is made of acrylic cone, 7 inches thick, the strongest transparent material available in 1960. The plan is simple, at least in concept. Fill the float with gasoline, which is lighter than water and incompressible, providing buoyancy. Attach steel ballast pellets to the bottom, held in place by electromagnets. Descend by releasing buoyancy or waiting for gravity to pull you down. When you want to come back up, release the ballast. The gasoline float will carry you to the surface. No engines, no complex systems, just ballast and buoyancy, gravity and float. It's elegant in its simplicity. But simplicity doesn't mean safe. At 9:30 in the morning, the Trieste is towed out to a position above the Challenger Deep. The weather is rough, swells are high, the support ship is pitching. Not ideal, but the window for the dive is closing. They've been preparing for months. Delays could mean cancellation. Picard and Walsh make the decision. We go today. They climb into the sphere. The hatch is sealed from the outside, bolted shut. They are now locked in. The only way out is up. They give the signal. The support crew releases the tow line. The Trieste begins to sink. The descent is slow, agonizingly slow. The Trieste doesn't have powerful thrusters to drive it down. It sinks at a rate of about 3 feet per second, roughly 2 miles per hour. At that rate, it will take nearly 5 hours to reach the bottom. 5 hours in a 7-foot sphere. No room to stand, no room to stretch. The temperature inside drops as the steel hull conducts cold from the surrounding water. Condensation forms on the walls. It's dark. The only light is from the instruments and a single external floodlight, which illuminates nothing but empty water and the occasional drifting particle of marine snow. At 1,000 feet, they pass through the thermocline. The water temperature drops sharply. The hull groans. The steel is contracting. Picard and Walsh exchange looks. This is normal. They've tested the sphere. It's rated for far more than this. But hearing your life support system groan is never comforting. At 3,000 feet, they enter the midnight zone. The last traces of sunlight disappear. Outside, the water is ink black. The pressure is now 90 times atmospheric pressure, enough to crush an unprotected human instantly. Inside the sphere, the air pressure is normal, 1 atmosphere. But the men can feel the weight of the water above them. It's psychological, but it's real. 3,000 feet of ocean pressing down. And they're only a fraction of the way to the bottom. They continue sinking. 4,000 feet, 5,000, 6,000. The numbers tick upward on the depth gauge. The pressure increases. The hull continues to groan. Occasionally, they hear sharp cracks, the sound of metal under stress, small adjustments as the steel compresses. It's normal. It's expected. But every crack makes them flinch. At 20,000 feet, 4 miles down, they're deeper than any human has ever been. Deeper than any submarine. Deeper than the crushed depth of every naval vessel ever built. They are in a realm where pressure is so extreme that it defies intuition. The water outside is not just pressing on the hull. It's trying to force its way in through every microscopic imperfection, every weld, every seal. The Trieste is a bubble of air in a universe of crushing force. And it's still sinking. At 30,000 feet, something happens. A loud, sharp bang. The entire sphere shudders. Both men freeze. That was not a normal sound. That was not steel groaning. That was structural failure. Something broke. They immediately check the instruments. Depth gauge, stable. Pressure inside the sphere. Normal. No alarms. No leaks. But something made that noise. Picard moves to the viewport and presses his face against the acrylic, trying to see the outside of the float above them. It's difficult. The viewport looks downward, toward the abyss. He can't see much of the superstructure, but he sees movement, something shifting. Debris, maybe, or a piece of the float. Walsh checks the ballast release system. Functional. They could abort right now, drop the ballast and shoot back to the surface. But they don't know what broke. If it's critical, aborting might not help. If the float is damaged, dropping ballast might cause catastrophic failure during ascent. And if it's not critical, aborting now means the mission fails. Years of preparation, millions of dollars. The deepest point on Earth unreached. They have to make a decision. Do we continue or do we go back? Picard looks at Walsh. Walsh looks at Picard. They've come 30,000 feet. They're 5,000 feet from the bottom, 15 minutes away from making history, and they have no idea what broke. Picard makes the call. We keep going. It's either the bravest or the most reckless decision in the history of deep-sea exploration. Probably both. They don't know if the Trieste will hold together for another 5,000 feet. They don't know if they'll be able to surface. But they've come too far to turn back based on a single noise. So, they sink. Deeper. Into the unknown. 35,000 feet. The depth gauge is approaching its maximum range. The pressure outside is now over 16,000 pounds per square inch. The Trieste's steel sphere is compressing, shrinking. The diameter has decreased by a fraction of an inch. The men inside don't notice, but the metal does. It's holding, barely. The engineering is working, but there's no margin for error. Any flaw, any crack, any imperfection in the welds, and the sphere will implode. Instantaneously. The men inside wouldn't even have time to realize they were dying. At 10:20 a.m., 4 hours and 48 minutes after leaving the surface, the Trieste touches the bottom. 35,797 feet. The deepest point a human being had ever reached. Picard and Walsh are now the two most isolated people in human history. Farther from help than astronauts in orbit. If something goes wrong, no one can reach them. There is no rescue, no backup. They are alone. They peer through the viewport. The external floodlight is on, casting a pale cone of light onto the sediment. The bottom is flat, pale, covered in fine, soft ooze. Diatomaceous remains, the skeletons of microscopic plankton that have been raining down from the surface for millions of years, accumulating in a thick blanket. The sediment is disturbed by their landing, swirling up in slow clouds. They wait for it to settle, and then Walsh sees something. Movement. He leans closer to the viewport. There, on the sediment, just at the edge of the light, a shape, flat, about a foot long. It's moving, slowly, deliberately, and it has eyes. Walsh calls Picard over. Both men stare. It's a fish, unmistakably. A flatfish like a sole or flounder, lying on the bottom, looking at them at 35,000 feet, where the pressure should make vertebrate life impossible, where bones should shatter and proteins should denature. There's a fish. They watch it for a few seconds, and then it swims away, disappears into the darkness beyond the light. Picard and Walsh spend 20 minutes on the bottom, taking photographs, recording observations, checking equipment. The Trieste is stable. Whatever broke during the descent doesn't seem to be affecting their ability to surface. They decide it's time to go. They activate the ballast release. The steel pellets drop away, and the Trieste begins to rise. The ascent takes 3 hours and 15 minutes, faster than the descent. The gasoline float, no longer weighed down, pulls them upward. The men sit in silence, exhausted, cold, relieved. When they finally break the surface, the support ship is waiting. They open the hatch. Fresh air rushes in. They made it, and immediately they report what they saw. A fish at the bottom of the Challenger Deep. Vertebrate life at the deepest point on Earth. The problem is, no one has seen it since. Not in 60-plus years. Not during James Cameron's dive in 2012. Not during any of the dozens of robotic missions that have visited Challenger Deep since. Every high-definition camera, every submersible, every baited trap, nothing. No fish. For decades, scientists debated what Picard and Walsh actually saw. The consensus, eventually, became that they were mistaken, that what they saw was not a fish, but a sea cucumber, a holothurian. These are invertebrates related to starfish and sea urchins. They're common at extreme depths, and some species are flat and elongated. In low light, through a small, thick viewport, after hours in a cramped sphere under immense stress, it's plausible that a sea cucumber could be mistaken for a flatfish. But Picard and Walsh never accepted this explanation. Until their deaths, both men insisted they knew what they saw. It was a fish. It had eyes. It had fins. It moved like a fish. And they were scientists, trained observers. They weren't prone to hallucination or error. So, what did they see? 3 possibilities. 1, they were wrong. It was a sea cucumber. 2, they saw a fish, but it was a transient visitor passing through, and it's never been seen again because it doesn't live there. 3, they saw something that does live there, but it's so rare, or so adept at avoiding cameras and traps, that we haven't found it in 60 years of looking. None of these explanations are satisfying, but that's the deep ocean. It doesn't care about satisfying us. What we do know, definitively, is that vertebrate fish do live at extreme depths, just not at Challenger Deep. In 2017, a team led by Alan Jameson from Newcastle University filmed a species of snailfish, Pseudoliparis swirri, at a depth of 8,178 meters, over 26,000 feet, in the Mariana Trench. Not at Challenger Deep, but in a shallower section. And this fish, Officially designated the Mariana snailfish, holds the record, the deepest living fish ever observed. The Mariana snailfish is bizarre, translucent, pale pink, gelatinous. It has no scales. Its bones are barely calcified, more cartilage than bone. Its skull is open with gaps. It looks fragile, delicate, like it would fall apart if you touched it. And in a sense, it would. Because this fish is built for pressure. Remove the pressure and it fails. Bring it to the surface and it doesn't explode like popular myth suggests. It melts. The tissues lose cohesion. The structure collapses. The fish becomes a puddle of organic goo. This is the paradox of deep sea life. It's not built to withstand pressure. It's built from pressure. Pressure is part of its structural integrity. The snailfish's cells are filled with organic molecules called piezolites, which stabilize proteins under high pressure. At depth, these molecules hold everything together. At the surface, without pressure, they don't work. The fish disintegrates. But even the snailfish has a limit. 8,178 meters is the deepest confirmed sighting. That's still 2,816 meters shallower than Challenger Deep, almost 2 miles shallower, and that difference matters. Because there's a hard biological limit to how deep vertebrate fish can survive. The limit is determined by a molecule called TMAO, trimethylamine N oxide. It's a small organic compound that deep-sea fish produce in high concentrations. TMAO acts as a pressure protectant. It stabilizes proteins and cell membranes under extreme pressure, preventing them from denaturing. The deeper the fish lives, the more TMAO it needs. But TMAO concentration can't increase indefinitely. At some point, the amount of TMAO required to protect against pressure becomes so high that it interferes with cellular function. The cell becomes too crowded, too viscous. Biochemical reactions slow down or stop. The limit, according to research by Paul Yancey at Whitman College, is somewhere around 8,200 to 8,500 meters. Below that depth, vertebrate life, as we know it, cannot exist. The pressure wins. So the deepest fish, the Mariana snailfish at 8,178 meters, is living right at the edge, the absolute limit. Any deeper and the biochemistry fails. And from 8,000 meters to the bottom of Challenger Deep, at nearly 11,000 meters, there are no fish, only invertebrates. Creatures that have evolved completely different strategies to cope with pressure. And this is why most scientists believe Pickard and Walsh were wrong. A fish at 10,994 meters shouldn't be possible. The TMAO limit says it can't happen. The absence of any other sightings suggests it didn't happen. And the likeliest explanation is misidentification. But then again, we've only explored a fraction of 1% of the deep ocean. We've spent more money, sent more people, and devoted more resources to exploring the surface of the moon than we have to exploring the Mariana Trench. It's closer, but it's harder. And maybe, just maybe, there are things down there we haven't figured out yet. Strategies for surviving pressure that we haven't imagined. Biochemistry that doesn't follow the rules we've written. The deep ocean has a way of humbling us. Every time we think we understand the limits of life, something down there proves us wrong. So, let's talk about the things we know do live at the bottom, the invertebrates, because they are, in their own way, even stranger than any hypothetical fish. Start with amphipods. On the surface, in shallow water, amphipods are tiny shrimp-like crustaceans, sand fleas, beach hoppers. Most are less than a centimeter long. Unremarkable. But in the deep ocean, amphipods become monsters. In 2016, a baited trap deployed at over 10,000 meters in the Kermadec Trench, just south of the Mariana, was recovered covered in amphipods. Not a few, thousands, swarming over the bait like locusts. And they were enormous. The largest individuals measured 34 centimeters, over a foot long, 10 to 20 times the size of their shallow water relatives. This phenomenon is called deep sea gigantism, and it's been documented across multiple species and multiple ocean trenches. Amphipods, isopods, mysids, all growing to sizes that would be impossible at the surface. And we don't fully understand why. Several theories exist. One involves Kleiber's law, which relates body size to metabolic rate. In cold, high-pressure environments, metabolism slows down dramatically. Slower metabolism means longer lifespans. And if an organism keeps growing throughout its life, even slowly, living for decades or centuries, means it gets big, really big. Another theory involves oxygen efficiency. Pressure affects how gases dissolve in water. At extreme depth, oxygen saturation behaves differently. Some researchers believe deep-sea creatures may be able to extract oxygen more efficiently from the water under pressure, allowing for larger body sizes despite low oxygen availability. A third theory is about food scarcity. The deep ocean is a desert. Food is rare. When it arrives, usually as marine snow or the occasional large carcass, competition is fierce. A larger body allows for greater energy storage, fat reserves, the ability to survive long periods between meals. In an environment where you might not eat for months, being big is an advantage. Whatever the reason, the result is unsettling. Imagine dipping your hand into what looks like empty black water and having it covered in foot-long shrimp, their needle-like legs clinging to your skin, their black eyes staring. That's the reality at the bottom of the trench. The darkness is full of scavengers, waiting, hungry. And then there are the Xenophyophores, single-celled organisms. Technically, they're giant protozoans. But calling them single-celled doesn't capture how bizarre they are, because these single cells are enormous. Some species grow to over 10 centimeters in diameter, 4 inches. That's the size of a dinner plate, one cell. They have no brain, no organs, no nervous system, just a single nucleus surrounded by cytoplasm, enclosed in a test, a shell-like structure that the organism builds from scavenged materials, sand grains, fragments of shells, mineral particles. The Xenophyophore secretes an organic glue and assembles these fragments into architectural structures, domes, tubes, lattices. Each species builds a different design, and they're doing this without a brain, without intent. It's purely chemical, genetic programming expressed through molecular interactions. But the result looks planned, designed, like something built by intelligence. And yet, it's just one cell following chemical gradients, constructing a protective shell from garbage. Xenophyophores are among the most common organisms at the bottom of the trench. They carpet the sediment, thousands of them, hundreds of thousands, building their structures, filtering the water for bacteria and detritus. Existing in a way that challenges our understanding of what a cell can be. Because how do you define life when one cell can grow to the size of your hand? When it can build architecture? When it survives in an environment that would kill almost anything else? The Xenophyophores force us to reconsider our categories. They're not animals, not fungi, not plants. They're something else, something that thrives in conditions we can barely tolerate in a steel sphere. And speaking of extreme conditions, let's talk about the hydrothermal vents. In 1977, scientists diving in the submersible Alvin discovered something off the coast of the Galapagos Islands that changed biology forever. Black smokers, hydrothermal vents, fissures in the seafloor where superheated water, heated by magma beneath the crust, erupts into the freezing ocean. The water coming out of these vents is over 400 degrees Celsius. Hot enough to melt lead, it's loaded with dissolved minerals, sulfides, metals, toxins. It's acidic. It's black with precipitating particles. And surrounding these vents, in an environment that should be sterile, there are ecosystems, tube worms, clams, mussels, shrimp, crabs, thriving. Not just surviving, thriving. And they're not eating each other, they're eating bacteria, chemosynthetic bacteria. Bacteria that derive energy not from sunlight, but from the chemicals in the vent water. Hydrogen sulfide, methane. These bacteria are the base of the food chain, and everything else feeds on them. This was revolutionary. Before 1977, we thought all life on Earth ultimately depended on the sun. Photosynthesis, plants and algae capturing sunlight, converting it to chemical energy, and everything else eating plants or eating things that eat plants. Solar energy flowing through the biosphere. But the vent ecosystems proved that wrong. Life can exist without sunlight, entirely. Chemosynthesis works just as well. Better, even, in some environments. And the Mariana Trench has hydrothermal vents, active ones, discovered in recent years by robotic submersibles, which means there are ecosystems down there that don't depend on the surface at all. They're energetically isolated, self-sufficient. If the sun went out tomorrow, these ecosystems would be fine. They'd keep going for millions of years until the Earth's interior cooled and the vents shut down. This has profound implications for astrobiology, because if life doesn't need the sun, then it doesn't need to be on a planet's surface. It can exist in subsurface oceans, under ice, in the dark. And suddenly, places like Europa, one of Jupiter's moons, become interesting. Europa has a liquid water ocean beneath an ice shell, and that ocean is in contact with a rocky core, which means it could have hydrothermal vents. And if it does, it could have life. Life that looks, biochemically and ecologically, a lot like the life at the bottom of the Mariana Trench. The trench isn't just the deepest place on Earth. It's a laboratory, a natural experiment in extreme life, a preview of what we might find when we finally send probes to Europa or Enceladus. And every organism we discover in the trench expands our understanding of where life can exist and what forms it can take. But here's the problem. We're destroying it before we finish studying it. In 2018, a team of researchers led by Alan Jameson published a study in the journal Marine Pollution Bulletin. They had collected amphipods from 6 of the deepest ocean trenches on Earth, including the Mariana. They brought the specimens back to the lab and analyzed their tissues for contamination. Specifically, they were looking for persistent organic pollutants, PCBs, polychlorinated biphenyls, industrial chemicals that were widely used in the 20th century before being banned in most countries due to their toxicity and persistence in the environment. What they found was shocking. Every single amphipod they tested contained PCBs, 100% contamination rate, and the concentrations weren't trace amounts, they were high. In some specimens, the PCB levels were 50 times higher than in amphipods collected from heavily industrialized coastal waters. The most polluted bay in China had lower contamination levels than the bottom of the Mariana Trench. How? How do industrial pollutants from factories and cities end up at the deepest point on Earth? The answer is marine snow. We've talked about marine snow before, that constant rain of organic particles drifting down from the surface. Dead plankton, fecal pellets, mucus, fragments of larger organisms. But marine snow isn't just organic. It's sticky, and as it falls, it collects things, including microplastics, including chemical pollutants that have adsorbed onto plastic particles. PCBs don't dissolve well in water, but they do bind to organic matter and plastics. So when a microscopic fragment of plastic coated in PCBs gets incorporated into marine snow, it sinks, slowly, over weeks or months, and eventually it reaches the bottom, where it settles into the sediment. And amphipods, those giant scavengers, eat the sediment. They ingest the plastic. The PCBs bioaccumulate in their tissues, and then snailfish eat the amphipods, and the PCBs move up the food chain. This is how Cameron's plastic bag got there. Passive sinking. It probably didn't fall as a bag. It probably fragmented into microplastics first, broken down by UV light and wave action at the surface. Then the fragments sank, individually, over years, accumulating at the bottom. And that grocery bag Cameron saw? Either it was unusually intact, or it represented billions of microplastic fragments that we couldn't see on camera. A visible symbol of invisible contamination. But plastics are just the beginning. Because the Mariana Trench has another contamination problem, one that's even more dangerous. And it was kept secret for decades. Between 1946 and 1993, the United States, Soviet Union, United Kingdom, France, and several other nations dumped radioactive waste into the ocean, massive quantities. By some estimates, over 200,000 tons of radioactive material, mostly low-level waste, contaminated equipment from nuclear reactors and weapons facilities, sealed in steel drums, dropped overboard, allowed to sink. The logic was simple. The ocean is huge. The waste will be diluted. The steel drums will contain the radioactivity for decades, long enough for the isotopes to decay to safe levels. And the deep ocean, cold and dark and isolated, seemed like the perfect disposal site. Out of sight, out of mind, forever. Except steel drums aren't designed for deep ocean pressure. At 1,100 atmospheres, steel corrodes rapidly. Seawater is aggressive. It finds weaknesses, rust, cracks, and the drums leak. Not might leak, do leak. And when they leak, radioactive material enters the environment. In 2016, a study by researchers from the Woods Hole Oceanographic Institution analyzed sediment samples from the Mariana Trench. They were looking for cesium-137 and plutonium isotopes. Both are products of nuclear fission. Both are highly radioactive. Both have half-lives measured in decades to thousands of years. And both were found in the sediment, in concentrations higher than background levels. The source? Almost certainly dumped nuclear waste. The drums are down there, corroding, leaking, and the radioactive isotopes are being incorporated into the sediment, where they're ingested by organisms, where they enter the food chain, where they accumulate. Now, the levels detected aren't immediately catastrophic. They're elevated, but not at levels that would cause acute radiation sickness in larger organisms. But that's not the concern. The concern is bioaccumulation. Isotopes like cesium and plutonium concentrate as they move up the food chain. An amphipod ingests a small amount. A snailfish eats 100 amphipods. A larger predator eats 100 snailfish. By the time you reach the top of the food chain, the concentration is orders of magnitude higher than in the environment. And here's the kicker. We don't know where all the drums are. The dumping was done hastily. Records are incomplete. Some nations didn't keep records at all. We have rough estimates of where the major disposal sites were, but exact locations, depths, how many drums, what isotopes, unknown, classified, lost to history. So the Mariana Trench, the most remote place on Earth, is contaminated with industrial chemicals from the 1950s and radioactive waste from the Cold War. And we didn't even know about most of this until the last decade. Because we hadn't looked. We assumed the deep ocean was too far, too isolated, too extreme to be affected by human activity. We were wrong, but it gets worse. Because contamination from past mistakes is one thing. What we're planning to do next is another. In the last 10 years, interest in deep-sea mining has exploded. Not metaphorically, literally. Dozens of companies backed by governments and investors are racing to extract minerals from the deep ocean floor. The target? Polymetallic nodules, manganese nodules. These are potato-sized rocks that form on the abyssal plains through a slow process of mineral precipitation. They're rich in manganese, nickel, cobalt, copper, and rare earth elements. Exactly the materials needed for batteries, electronics, and renewable energy technology. On land, these materials are becoming scarce. Mines are depleting. Demand is increasing. And the ocean floor is covered in them. Trillions of nodules, just lying there, waiting to be harvested. It's a gold rush. Except it's 7 miles underwater. The technology to harvest these nodules is already being developed. Massive robotic crawlers, the size of small buildings, equipped with rotating drums and suction systems. They drive across the seafloor, scooping up nodules and sediment, pumping the mixture to a surface ship where the nodules are separated and the sediment is discharged back into the ocean. Simple, efficient, profitable, and ecologically catastrophic. Because those nodules aren't just rocks. They're habitat. Organisms live on them, attached to them. Use them as substrate in an environment where hard surfaces are rare. Xenophyophores, sponges, corals. Remove the nodules and you remove the habitat. The crawlers don't discriminate. They take everything. And what they leave behind is a scoured, barren plain. Sediment churned into suspension, creating plumes that drift with currents, smothering organisms kilometers away. The disturbance is total, and we have no idea how long recovery takes, because the deep ocean is slow. Growth is slow. Reproduction is slow. A sponge at the surface might reach maturity in a few years. A deep-sea sponge might take a century. Remove it, and it's gone for lifetimes. Human lifetimes. And the nodules themselves, they grow at a rate of millimeters per million years. Once you remove them, they're gone. Effectively forever. But the mining companies aren't deterred, because there's money to be made, and the regulatory framework is weak. Most of the deep ocean, including much of the Mariana Trench, is in international waters, beyond any nation's jurisdiction, which means it's governed by the International Seabed Authority. the ISA, a UN body based in Jamaica. The ISA's mandate is to manage seabed resources for the benefit of all humanity. In practice, that means issuing exploration and exploitation licenses to companies and nations. And in the last 5 years, the ISA has issued dozens of exploration licenses. China, Russia, the UK, France, Japan, South Korea, private companies, all have claims, all are exploring. And the ISA is under pressure to finalize regulations that would allow full-scale commercial mining to begin. The target date, as of 2023, is within the next few years. Some companies are hoping to start extraction by 2025, which means the clock is ticking, and the regulations being written are, according to many scientists, woefully inadequate. Because the ISA is under conflicting pressures. It's supposed to protect the marine environment, but it's also supposed to facilitate resource extraction. And those goals are incompatible. You cannot mine the seafloor without causing massive environmental damage. The question isn't whether damage will occur. The question is how much we're willing to accept, and who decides. In 2009, the United States took a step that seemed protective. President George W. Bush, in one of his final acts in office, designated the Mariana Trench Marine National Monument. Over 95,000 square miles of ocean, including the Challenger Deep, protected from exploitation. No fishing, no mining, no oil drilling. It sounded like a victory for conservation. But there's a catch. The monument only covers the portion of the trench within US territorial waters. The United States claims the area around Guam and the Northern Mariana Islands. But most of the trench, including significant portions of the Challenger Deep region, is in international waters, outside the monument, under ISA jurisdiction. So the monument protects some of the trench, but not all. And sediment plumes don't respect boundaries. If mining operations start just outside the monument, in international waters, the sediment they churn up will drift. Currents will carry it, and it will settle inside the protected area, contaminating it. There's no way to prevent that. The ocean is fluid. Borders are imaginary lines on maps. Physics doesn't care. And enforcement? How do you patrol 7 miles down in complete darkness across thousands of square miles? You don't. The monument is symbolic, important symbolically. But practically, it's a line on a map, and the mining companies are preparing to work right up to that line, and possibly over it if they think they can get away with it. So here's where we are, the deepest place on Earth, the last true wilderness, contaminated with plastics, industrial chemicals, and radioactive waste from the 20th century. And now, in the 21st century, we're preparing to industrialize it, to mine it, to turn it into a resource extraction zone before we've even finished cataloging what lives there. We've explored less than 1% of the Mariana Trench. Less. We've sent submersibles to a handful of locations. We've dropped cameras and traps. We've collected samples. But the trench is 1,500 miles long and up to 43 miles wide. We've looked at a few spots for a few hours each, and based on that, we're making decisions about whether to allow industrial activity. It's insane. It's like exploring 1 square mile of the Amazon rainforest and then deciding you know enough to start clear-cutting. Except worse. Because the Amazon, at least, we can see. We can walk through it. Study it. The trench is invisible, inaccessible. We're making decisions about a place we fundamentally do not understand. But there's hope. Not in regulation, not in the ISA, which is structurally compromised. Hope in technology. Because the same technological advances that are enabling deep-sea mining are also enabling something else. Cheap, autonomous, robotic exploration. At scale. For decades, deep-sea exploration was limited by cost. Every submersible dive cost millions of dollars. You needed a surface ship, a crew, specialized equipment. Manned submersibles like Trieste or Deep Sea Challenger were one-offs, built for single missions. Unmanned ROVs, remotely operated vehicles, were cheaper but still expensive, still required ships and pilots and support infrastructure. But that's changing. The revolution is in autonomy, in artificial intelligence, in swarm robotics. Instead of building one expensive submersible and sending it down once, you build 100 cheap robots. Small, expendable, autonomous. You program them with AI navigation systems. You deploy them. And they explore. On their own. No surface ship needed after deployment. No pilots. No real-time control. The robots navigate using onboard sensors. They communicate with each other in a mesh network. If one finds something interesting, it calls the others. They swarm, investigate, record data, and when their batteries run out, they surface. Or they don't, because they're cheap. Losing a few is acceptable. This approach is inspired by biology, by the way social insects explore. Ants don't have a central command. Each ant follows simple rules. When you combine hundreds of ants, following simple rules, you get complex intelligent behavior, swarm intelligence, and we're applying that to robots. Several institutions are already developing these systems. The Schmidt Ocean Institute, NOAA, MIT. Soft-bodied robots inspired by jellyfish and squid that can compress to fit through tight spaces, that can withstand pressure without rigid hulls, that are cheap to manufacture and deploy in large numbers. The goal is to flood the trench with sensors, autonomous explorers, create a persistent presence, not one dive every few years, but continuous observation. Hundreds of robots, combing the seafloor, recording everything, uploading data via acoustic modem to surface buoys. And this technology is coming online in the next few years. Some prototypes are already being tested. By 2025, we could have swarms operational, which means for the first time, we'll have comprehensive data on the trench ecosystem. What lives there? Where? How many? What they eat? How they reproduce? We'll finally start to understand what we're about to destroy, because that's the race. Understanding versus exploitation, science versus profit. And right now, profit is winning. The mining companies are ready. The equipment is built. The licenses are being issued. The regulations are being finalized. And science is scrambling to catch up, to document what's there before it's gone. It's a depressingly familiar story, except this time it's not a rainforest or a coral reef. It's the deepest, darkest, most alien place on Earth, and we're going to turn it into a strip mine. But let's talk about why this matters beyond Earth. Because the Mariana Trench isn't just important for its own sake. It's important for astrobiology, for understanding life elsewhere in the solar system, and possibly beyond. Europa, one of Jupiter's 4 large moons. From the surface, it looks like a cracked ice ball, pale, smooth in some areas, fractured in others, long dark streaks crisscrossing the surface. Those streaks are cracks in the ice shell, and beneath that shell, confirmed by magnetic field measurements and tidal flexing data, is a liquid water ocean. The ice shell is estimated to be 10 to 15 miles thick. Beneath it, an ocean 100 miles deep, deeper than any ocean on Earth. And that ocean is in direct contact with Europa's rocky core, which means there's a boundary between water and rock. And where water meets rock, chemistry happens. Minerals dissolve, elements mix. And if there's heat from tidal flexing caused by Jupiter's immense gravity, you get hydrothermal vents, black smokers, exactly like the ones in the Mariana Trench. And if there are vents on Europa, there could be life. Chemosynthetic ecosystems, bacteria metabolizing sulfides and methane, larger organisms feeding on the bacteria, an entire biosphere existing in complete darkness under miles of ice without any energy from the sun. Just like the vent ecosystems in the trench. In fact, if we find life on Europa, the best bet is that it will look, biochemically and ecologically, very similar to trench life, because the constraints are the same: high pressure, low temperature, no light, chemical energy from vents. Evolution, operating under the same constraints, tends to produce similar solutions. Convergence. So every organism we study in the Mariana Trench teaches us something about what to look for on Europa, how to recognize biosignatures, what metabolic pathways are possible, what morphologies work under extreme pressure. The trench is our training ground, our analog site, the closest thing we have to a Europa Ocean that we can actually visit. And Enceladus, another moon. This one orbiting Saturn, smaller than Europa, but even more interesting in some ways, because Enceladus has plumes, jets of water vapor and ice particles erupting from cracks at the South Pole. Cassini, the spacecraft that studied Saturn for 13 years, flew through those plumes, analyzed their composition, and found organic molecules, salts, silica nanoparticles, everything indicating a subsurface ocean in contact with a hot rocky core. Enceladus is easier to study than Europa in one crucial way. You don't have to land. You don't have to drill through miles of ice. You just fly through the plume, collect samples, analyze them. If there's life in Enceladus's ocean, it might be detectable in the plume material: bacteria, organic molecules, chemical signatures of metabolism. And again, the Mariana Trench is the analog. If we want to know what Enceladus's ocean looks like, we study the trench. If we want to know what life there might look like, we study vent ecosystems. If we want to design instruments to detect that life, we test them in the trench. NASA knows this, which is why they're increasingly interested in deep-sea research. The technology being developed to explore the trench, autonomous robots, pressure-resistant sensors, AI navigation, is directly applicable to Europa and Enceladus missions. Some of the same engineers are working on both, the same institutions. Schmidt Ocean Institute collaborates with JPL. NOAA works with NASA's astrobiology program. The overlap is significant, and there are missions planned. Europa Clipper, launching in 2024, will orbit Europa and study the ice shell. Look for thin spots, map the surface, identify potential landing sites. Europa Lander is in the proposal stage. Would land on the surface, drill through the ice, and lower a probe into the ocean. That probe would use technology derived from deep-sea submersibles, pressure hulls, acoustic communication, chemosynthesis detectors, all tested in the Mariana Trench. So the trench is more than just a hole in the ocean floor. It's a scientific resource, a natural laboratory, a place where we can test our theories and our technology against the most extreme conditions Earth has to offer. And what we learn there will guide our search for life beyond Earth. But only if the trench remains intact, only if we don't destroy the ecosystems before we understand them, only if we prioritize science over profit. And right now, that's not a given. Because here's the timeline: 1960. First, humans reach Challenger Deep, spend 20 minutes, see a fish that no one has seen since. 2012. James Cameron reaches the bottom, finds a plastic bag, spends 3 hours, sees no large life. 2014 to 2018. Multiple robotic missions, landers, cameras, traps, collect organisms, discover 100% microplastic contamination, detect radioactive isotopes, document ecosystem. 2023. International Seabed Authority finalizes mining regulations. Exploration licenses issued. 2025. First commercial mining operations projected to begin. 65 years from first human contact to industrialization. That's the timeline. And in that 65 years, we've explored less than 1% of the trench. We've documented a few dozen species. We've dropped cameras in a handful of locations. We've collected samples from a tiny fraction of the seafloor. And based on that, we're comfortable starting to mine it, starting to extract resources, starting to fundamentally alter the environment before we know what's there, before we understand the ecology, before we've even finished basic exploration. It's the same pattern we've followed on land. Explore a little, extract a lot, realize too late what we've lost. Except on land, we can sometimes restore, replant forests, reintroduce species, clean up contamination. It takes decades or centuries, but it's possible. In the deep ocean, there is no restoration. Remove a nodule field, and it's gone for millions of years. Wipe out a vent ecosystem, and the species might be globally extinct because vent communities are isolated. There's no recolonization, no recovery, and the trench is small. Geologically, it's enormous, 1,500 miles long. But ecologically, it's fragile. It's isolated, it's specialized. Every species there is adapted to extreme conditions. They can't live anywhere else. They're endemic. And endemic species, by definition, are vulnerable, lose their habitat, and they're gone forever. So what do? How do we balance the need for resources, which is real, with the need to protect irreplaceable ecosystems? That's the question. And there's no easy answer. Some scientists argue for a moratorium. Stop all mining activity until we've completed comprehensive surveys of the ocean floor. Map it, document it, understand it, then make decisions. This is the precautionary principle. When you don't know the consequences, don't act. Gather information first. Others argue that's unrealistic. Surveying the entire ocean floor would take decades. Maybe a century. We need those resources now, for batteries, for renewable energy, for the green transition. We can't wait 100 years, so we have to accept some environmental cost. The question is how much and where. A compromise position is strategic protection. Identify key areas, vent systems, nodule fields with high biodiversity, areas that are scientifically valuable or ecologically critical. Protect those, make them off-limits to mining, and allow extraction in less sensitive areas. This is the Marine Protected Area approach. It's not perfect, but it's better than nothing. The problem is defining less sensitive. because we don't know enough to make that determination. Every time we explore a new section of seafloor, we find something unexpected, a new species, a new ecosystem. How do you protect what you haven't discovered yet? And even if we could identify the critical areas, enforcement is a nightmare. The deep ocean is vast, dark, remote. You can't patrol it. You can't monitor it. Mining companies operating in international waters could ignore protected areas, and no one would know until the damage was done. By the time satellites detect sediment plumes or acoustic sensors pick up mining equipment, it's too late. So the reality is, we're probably going to lose ecosystems. We're probably going to drive species extinct. We're probably going to damage the Mariana Trench. The question is how much, and whether we care enough to minimize it. The optimistic view is that public awareness can make a difference. The trench is charismatic in a weird way. People are fascinated by it. The deepest place on Earth, alien life, extreme conditions. That fascination can translate into political pressure, into regulations, into funding for research and protection. But awareness is a double-edged sword, because the same fascination that drives conservation also drives exploitation. Billionaires want to visit the trench. Companies want to extract resources. Tourists want footage. Everyone wants a piece of the mystery. And every interaction, every visit, every extraction changes it, alters it, makes it a little less pristine, a little less wild. There's a concept in environmental ethics called the tragedy of the commons. When a resource is shared and no one owns it, everyone has an incentive to exploit it, and no one has an incentive to protect it. Because protection costs you individually, but benefits everyone. Whereas exploitation benefits you individually and costs everyone. So rational actors, acting in their own self-interest, over-exploit shared resources until they collapse. The Mariana Trench is a commons. No one owns it. Everyone has access. And unless there's strong international governance, which there isn't, the tragedy is inevitable. But let's end on a less depressing note. Because despite everything, despite the contamination and the threats and the ignorance, the trench still holds wonder. It still has secrets. And we're still exploring. In 2020, the Chinese submersible Fenduji, which means striver, reached the bottom of Challenger Deep multiple times. It spent hours on the seafloor, collected samples, took video, and found things. New species, unusual formations, details that are still being analyzed. In 2021, Victor Vescovo, an American explorer and investor, completed the 5 Deeps expedition, reaching the deepest point in each of the 5 oceans, including Challenger Deep, which he visited multiple times in his submersible, the DSV limiting factor. He brought scientists, collected samples, documented life, and set a depth record reaching slightly deeper than Cameron, though the exact numbers are disputed due to measurement techniques. In 2023, unmanned landers from Japanese and American research institutions recorded footage of organisms never seen before, including a species of sea cucumber with bioluminescent properties, glowing. In the deepest darkness. Why? No one knows. There's no evolutionary pressure for bioluminescence where there's no light to see it, unless there are other organisms with eyes that we haven't found yet, predators, or prey, or both. Every mission finds something new, something unexpected, and that's the point. The trench is not fully explored, not fully understood, not fully documented, and until it is, we're gambling. Every decision to allow mining, to permit exploitation, is a gamble that we're not destroying something irreplaceable. And maybe we're okay with that gamble. Maybe we've decided, collectively, that the resources are worth the risk. That batteries and electronics and green energy justify the loss of ecosystems we've barely seen. Maybe that's a rational trade-off. But let's at least be honest about what we're trading. Let's not pretend we're preserving the trench while we're preparing to mine it. Let's not pretend the monument protects anything when the currents don't respect borders. Let's not pretend we understand what we're destroying when we've explored less than 1%. Because the truth is, we don't know what's down there. We don't know what we're losing. And by the time we do know, it will be too late. The mining will have started. The ecosystems will be damaged. And we'll spend the next century trying to catalogue what we destroyed, wondering what we missed. The Mariana Trench is the last great mystery on Earth, the final frontier, and we're about to turn it into a mine. That's the reality. That's where we are. And unless something changes, unless we choose science over profit, understanding over extraction, wonder over greed, that's where we're going. So here's the question. Not what's at the bottom of the Mariana Trench. We're learning that, slowly. The question is, what kind of species are we? Are we explorers? Curious? Patient? Willing to wait for understanding before we act? Or are we exploiters? Impatient? Short-sighted? Willing to destroy what we don't understand for short-term gain? The trench will answer that question, one way or another, and the answer will define us, for better or worse. Jacques Picard and Don Walsh spent 20 minutes at the bottom in 1960. They saw a fish. They came back and told the world. And for 60 years, we've been arguing about what they saw, debating, investigating, trying to understand. James Cameron spent 3 hours at the bottom in 2012. He saw a plastic bag. He came back and told the world. And we shrugged, acknowledged it, and kept going. That's the difference. Mystery inspires investigation. Pollution inspires apathy. We care more about a fish that might not exist than about the garbage we know is there. And maybe that's human nature. Maybe we're wired to be fascinated by the unknown and indifferent to the known. But that's a problem, because the known, the plastic and the chemicals and the radioactive waste is destroying the unknown. And once the unknown is gone, there's nothing left to be fascinated by. Just a mine, a dump, an empty hole. The trench still has secrets, still has species we haven't found, still has ecosystems we haven't documented, still has wonder. But the clock is ticking. The mining equipment is being built, the regulations are being written, the licenses are being issued, and in a few years, maybe less, we'll start digging, start extracting, start destroying, and the mystery will become memory. That plastic bag is still there, at the bottom of Challenger Deep, deeper than Everest is tall, waiting, a symbol of our reach, our carelessness, our future. We got our garbage to the deepest place on Earth before we got our understanding there. And unless we change course, we'll industrialize it before we finish exploring it. The Mariana Trench, the last place on Earth we're polluting before we understand. The first place we'll mine before we finish studying. The final wilderness. About to become the first sacrifice. That's the story. That's the truth. And that's the choice we're making right now, whether we realize it or not.